Imagine looking up at the night sky and seeing a faint green glow dancing near the poles. That soft light is only the most visible sign of an invisible shield that surrounds our entire planet. Deep inside Earth is a vast ocean of liquid metal is swirling, generating a magnetic field that reaches far out into space and deflects the constant stream of charged particles flowing from the sun. Without this magnetic field, those particles would strip away the atmosphere over time and bathe the surface in harmful radiation. The same field traps some of those particles into donut-shaped regions known as the radiation belts, creating zones of intense energy that spacecraft must carefully navigate. Satellites equipped with magnetometers and particle detectors have mapped the strength and shape of the field, while ground stations record its slow change and sudden storms. Rock samples from the ocean floor and lava flows preserve the direction of the field from millions of years ago, showing that it had flipped polarity many times. Together, these observations reveal a dynamic system that protects life, shapes the upper atmosphere, and responds to the sun's activity. In the account of that follows, we will explore how the magnetic field is generated, how it interacts with the solar wind to form the magnetosphere, how the radiation belts arise and behave, and how the field itself can reverse its polarity over long periods, using clear language and the solid evidence that science has gathered, so the invisible forces around our planet become as understandable as the glow of the aurora. Every compass needle that points roughly north, every aurora that lights the polar skies, every satellite that survives the harsh environment of near-Earth space, and every ancient rock that records a reverse magnetic direction is part of the same continuous story of a living magnetic field powered by the planet's deep interior and constantly tested by the sun. Earth's magnetic field is produced by the motion of electrical conducting liquid metal in the outer core. The outer core is a layer of molten iron and nickel, roughly 2,260 kilometers thick, that surrounds the solid inner core. Heat escaping from the inner core and from radioactive decay keeps the outer core in constant motion. Hotter, less dense material rise, while cooler, denser material sinks, creating convection currents. Because Earth is rotating, these currents are twisted into complex helical patterns by the Coriolis effect. Moving electrical charges generate magnetic fields, and the swirling liquid metal acts like a self-sustaining dynamo. Once a weak field is present, it induces electric currents in the moving metal, which in turn strengthen the field, maintaining it against the natural tendency of magnetic fields to decay. The process is continuous and self-regulating. If the field becomes too weak, the induction weakens. If it grows too strong, the motions adjust. Laboratory experiment with liquid metal and numerical stimulation that solved the equations of fluid motion and electromagnetism under core conditions reproduce the main feature of the observed field, including its dipole dominance and its slow changes over time. The result is a magnetic field that all the surface looks roughly like the field of a giant ball magnet, tilted about 11 degrees from the rotation axis, with magnetic poles that do not coincide exactly with their geographic poles. Measurements of the field strengthened at the surface range from about 25 microtesla near the equator to more than 65 microtesla near the magnetic poles. The field is not perfectly symmetrical. There are regions of weaker and stronger intensity, and the magnetic poles wander slowly over time. One region of notably weak field currently exists over the South Atlantic, where the field strength is low enough that satellites passing through experience higher radiation doses. The same dynamo process that sustains the field can also cause it to reverse polarity. Over long periods, the flow patterns in the outer core can become unstable. The simple dipole field begins to weaken while more complex multiple components grow stronger. During this transitional state, the magnetic poles wander widely. Temporary poles can appear at low latitudes, and the overall field strength at the surface can drop to as little as 10 to 20% of its normal value. The transition itself typically lasts several thousand years. Although the exact duration varies from one reversal to another, eventually the multiple field organize into a new dipole that points in the opposite direction, and the field strength recovers. The process does not involve the field disappearing completely. A residual field of complex shape remains throughout the transition, continuing to provide some shielding. Evidence for this reversal is preserved in the magnetic minerals of rocks. When lava cools or when sediment settles, magnetic rains lock in the direction of the ambient field. Sequence of lava flows and deep-sea sediment cores show intervals of normal polarity, alternating with intervals of reverse polarity, with transitional direction recorded in the layers that form during the change. The seafloor became itself carries a strip pattern of the normal and reverse magnetization that's symmetrical about the mid-ocean ridges, providing a continuous record of polarity changes going back more than 100 million years. The average interval between reversals is a few 100,000 years, but the timing is irregular. Some periods show frequent flips, while others show long stretches of stable polarity lasting millions of years. These records demonstrate that reversals are natural and repeated feature of the dynamo, not a rare catastrophe. The magnetic field does not stop at the surface. It extends tens of thousands of kilometers into space, forming a region called the magnetosphere. On the sunward side, the continuous flow of charged particles from the sun, known as the solar wind, compress the field into a blunt shape. A bow shock forms where the supersonic solar wind is slowed and heated as it encounters the magnetic obstacle. Behind the bow shock lies the magnetopause, the boundary where the pressures of the solar wind balance the pressure of Earth's magnetic field. Under normal solar wind conditions, this boundary sits at about 10 Earth radii on the day side, but during strong solar events, it can be pushed inward to only a few Earth radii. On the night side, the field is stretched into a long magnetoidal tail that can extend millions of kilometers downstream. Inside this cavity, the magnetic field controls the motion of charged particles, guiding them along field lines and trapping some of them in closed orbits. The magnetosphere is not empty. It is filled with a tenuous plasma of ions and electrons that originate from the solar wind. The ionosphere and the radiation belts themselves, ground-based magnetometers, and networks of satellites continuously monitor the shape and strength of the magnetosphere. During periods of strong solar activity, the solar wind pressure increased, pushing the magnetopause closer to Earth and allowing more energy to enter the system. These disturbances can be seen as rapid changes in the magnetic field recorded at the surface as intensified auroral displays. The amount of energy transferred during a major geomagnetic storm can exceed the total energy of a large hurricane. Yet, it is delivered over a vast volume of space. Even during a polarity transition, when the surface field is weaker and more complex, a magnetosphere still forms, although its size and shape become more variable and its ability to stand off the solar wind is reduced. Within the magnetosphere, two main regions contain especially high concentration of energetic charged particles. These are the radiation belts. The inner belt is a relatively stable donut-shaped zone that begins a few thousand kilometers above the surface and extends outward to about 10,000 kilometers. It is populated mainly by high-energy protons, many of which are created when cosmic rays collide with atoms in the upper atmosphere and produce neutrons that later decay into protons. These protons can remain trapped for years because their high energies make them less susceptible to scattering by plasma waves. The outer belt is larger, more variable, and filled mainly with energetic electrons. It typically extends from about 13,000 kilometers to 60,000 kilometers or more, although its outer edge fluctuates with solar activity. Between the two belts lies a short slot region where particle intensities are lower because of the interactions that scatter particles out of their trapped orbits. The particles in both belts spiral along magnetic field lines, bounce back and forth between the northern and southern hemisphere, where the field strength increases, and also drift slowly around Earth. This three-part motion, gyration around the field line, bouncing between mirror points, and longitudinal drift, keeps them trapped for long periods, sometimes months or years, until collisions or wave particles interaction remove them. The bounce period for typical electron is on the order of seconds, while the drift around the Earth can take minutes to hours depending on energy and location. During a field reversal, the changing geometry of the magnetic field alters the trapping conditions, and the belts may become more diffuse or temporarily reconfigured. Yet, the basic mechanism of particle trapping continues as long as a magnetic field of a sufficient strength exists. The energy of the trapped particle is extremely high. Protons in the inner belt can reach energies of hundreds of millions of electron volts, while electrons in the outer belt commonly have energies of hundreds of thousands to several millions electron volts. These energies are far greater than those of ordinary thermal particles in the atmosphere of solar wind. When a spacecraft passes through the belts, its electronics and solar panels can be damaged by the constant bombardment of these particles. Since high-energy protons can flip bits in computer memory or degrade solar self-efficiency over time. Astronauts must limit their time in belts or stay within shield regions of the spacecraft. The belts are not static. Their intensity and location change in response to solar storms. A strong burst of solar particles or a sudden compression of the magnetosphere can inject fresh particles into the outer belt, temporarily increasing radiation level by factors of 10 or more. Over subsequent days and weeks, the excess particles gradually drains away through precipitation into the atmosphere or escape into interplanetary space. Satellites carrying particle detectors that have recorded these changes in real time, showing how the outer belt can almost disappear during some storms and then rebuild within hours or days. The rebuilding process involves the acceleration of lower energy electrons by plasma waves that transfer energy from the solar wind-driven plasma to the trapped population. Similar acceleration and loss processes would operate during a polarity transition, although the overall intensity and spatial distribution of the belts would reflect the weaker and more complex field of that time. The magnetic field and the radiation belts are intimately connected. The field provides the magnetic bottle that traps the particle, while the particles themselves carry electric currents that slightly modify the field. During magnetic storms, these currents become strong enough to produce measurable disturbance at the surface, known as geomagnetic storms. Such storms can induce electric currents in long power lines and pipelines, disrupt radio communications that rely on the ionosphere, and increase the drag on satellites by heating and expanding the upper atmosphere. The aurora is the most visible manifestation of the interaction, when energetic particles from the magnetosphere or the radiation belts follow field lines down into the upper atmosphere. They collide with oxygen and nitrogen atoms, exciting them and causing them to emit light. The characteristic green and red color of the aurora come mainly from oxygen at different altitudes, while nitrogen produces blues and purples. The location of the auroral oval shifts with intensity of the solar wind. During quiet times, they form rings around the magnetic poles at high latitude, and during storms, they expand toward lower latitudes, sometimes becoming visible from mid-latitude regions. The total power dissipated in a bright aurora can reach tens of billions of watts, energy that ultimately comes from the solar wind and is channeled by the magnetic field during a polarity reversal. The aurora zones would become more widespread and less tightly confined to the polar regions, because the field geometry itself would be more disordered. Evidence for the structure and behavior of the magnetic field and radiation belts comes from multiple independent sources. Networks of ground magnetometers measures the strength and direction of the field at the surface with high precision and have recorded its gradual change. Over more than a century, the magnetic poles have drifted tens of kilometers per year, and the overall strength of the dipole field has decreased by several percent since systematic measurement began. Ocean floor rocks and sequences of lava flows preserve the direction of the field at a time they cool, revealing that the field had reversed polarity hundreds of times in the past. During a reversal, the field does not disappear entirely, but becomes weaker and more complex for several thousand years before strengthening again in the opposite direction. The polarity reversals are recorded worldwide in the magnetic strips of the seafloor and sedimentary sequences on land, providing a continuous timeline that matched other dating methods. The average time between reversal is a few 100,000 years, but the interval is irregular. Some periods show frequent reversals, while others show long intervals of stable polarity. Intermediate direction recorded in transitional lava flows and sediments confirm that the change is gradual rather than instantaneous, and that a residual field persists throughout. In space, fleets of satellites equipped with magnetometer and particle sensors have mapped three-dimensional structure of the magnetosphere and the radiation belts in details. Measurements show that the inner belt is relatively stable, while the outer belt responds dramatically to solar activity. The energy spectra of the trapped particles, their pitch angle distributions, and the timing of their injections and loss all match theoretical prediction based on the motion of charged particles in a dipole-like magnetic field. When the solar wind is especially strong, the entire magnetosphere is compressed and the radiation belts can be depleted and then replenish within a single day. Events that have been observed and repeatedly by multiple spacecraft, ground-based radars, and optical instruments detect the precipitation of particles into the atmosphere as increased ionization and auroral light, confirming that the belts are continuously leaking particles along field lines. The combination of in situ particle measurements, remote sensing of the aurora, and ground magnetic records provide a consistent picture of how energy and particles flow through the system. The same methods applied to the rock record show that the fundamental trapping mechanism has operated through many polarity states. The magnetic field also plays a crucial role in protecting the atmosphere. Without it, the solar wind would gradually strip away lighter gases over geological time. Planets that lack a global magnetic field show evidence of significant atmospheric loss. On Earth, the magnetosphere deflects most of the solar wind around the planet. Although some energy and particles still enter through the polar cups and the magnetosphere, the radiation belts themselves are a byproduct of this protective system. They are the regions where particles that do penetrate are trapped and temporarily stored. Over long time scales, the field has remained strong enough to maintain this protection, even through polarity reversals, as shown by the continuous presence of an atmosphere and the survival of life through many reversal events recorded in the geological record. The field also shields the surface from a fraction of the galactic cosmic rays, high-energy particles that originate outside the solar system during periods of weak field. The cosmic ray flux at the surface increase, an effect recorded in the production rates of certain isotopes in the atmosphere and in ice cores. During a polarity transition, the increased cosmic ray flux would be temporary, lasting only as long as the field remains weak, and the residual field would still provide partial shielding. Variations in the field occur on many time scales. Daily changes are caused by electric currents in the ionosphere, driven by solar heating and tides. These quiet day variations are regular and predictable. Long-term secular variation reflects the slow evolutions of the flow patterns in the outer core and can be seen as the gradual drift of the magnetic poles and the weakening or strengthening of different parts of the field. Sudden storm time changes are driven by the solar wind and can alter the surface field by hundreds of nanotesla within minutes to hours. All of these variations are recorded both on the ground and in space, and they match the prediction of models that combine the internal dynamo with the external interaction with the solar wind. The strength of the surface field is sufficient to orient a compass needle. Yet the same field, when measured in space, is strong enough to stand off the solar wind at a distance of roughly 10 Earth radii on the day side under normal conditions. During extreme solar events, that distance can shrink to only a few Earth radii, allowing the radiation belts to move closer to the surface and increasing the radiation risk for satellite and low orbits. Historical records of geomagnetic storms, including that disrupted early telegraph systems, show that such extreme compression have occurred in the past and will occur again. A polarity reversal represents the extreme end of the same spectrum of variation, driven by internal core dynamics rather than external solar forcing. The particles in the radiation belts are not a static population. They are continually accelerated, scattered, and lost. Plasma waves generated by the interaction of the solar wind with the magnetosphere can push electrons to higher energies through a process of resonant interaction, while other waves can cause them to change their pitch angles so that they precipitate into the atmosphere. Protons in the inner belt have longer lifetimes because they are less easily scattered by the same waves. The balance between sources and losses determines the overall intensity of the belts at any given time. Observations during different phases of the solar cycle show that the outer belt is generally more intense during periods of high solar activity, although individual storms can produce both increase and decrease depending on the detailed conditions of the solar wind and the interplanetary magnetic field. These complex responses have been documented by long-term satellite missions that have measured particle flux over completed solar cycles, revealing patterns that repeated with 11-year solar cycle and with shorter recurrent solar wind streams. Similar source and loss processes would continue during a few reversals, modulated by the changing strength and geometry of the trapping field. The interaction between the magnetic field and the solar wind also creates a complex system of electric currents that flow through the magnetosphere and into the ionosphere. These currents close through the polar regions and produce the magnetic disturbance recorded on the ground. During a strong storm, the currents can induce electric fields at the surface that drive current in long conductors, such as power grids and pipelines, sometimes causing damage or operational problems. The same currents heat the upper atmosphere, causing it to expand and increase the drag on low-orbiting satellites, which must then use fuel to maintain their orbits. All of the effects are direct consequence of the coupling between the internal magnetic field and the external solar wind plasma, a coupling that is mediated by the magnetosphere and the radiation belts. During the polarity transition, the current system would become more irregular and the resulting surface disturbance more widespread. Yet the basic coupling mechanism would remain the same. In summary, Earth's magnetic field is a dynamic product of the liquid outer core that extends into space and creates a protective magnetosphere. Within that magnetosphere, the radiation belts form natural storage regions for energetic particles. The field can and does reverse its polarity through a gradual process of weakening, multiple growth, and reionization that lasts several thousand years. As recorded in rocks worldwide, the field and belts together shield the surface from the worst of solar wind and cosmic radiation, while producing the aurora and influencing the upper atmosphere. Continuous measurements from the ground and from space, together with the ancient record preserved in rocks, demonstrate that this system has operated for billions of years, varying in strength and direction, yet remaining effective enough to allow an atmosphere and life to persist even through many polarity reversals. The invisible magnetic shield and the energetic particle belts it contains are therefore essential features of the planet, linking the deep interior to the space environment in a continuous, measurable way. Every change in the solar wind, every shift in the core flows, every particle that spirals along the field lines, and every polarity transition recorded in the geological parts is part of ongoing interaction that can be observed, quantified, and understood through the combined evidence of satellites, ground instruments, and the rock record.